this class or about all the topics that we have been assigned. Okay, if you don't have anything, I will start the lecture today. And in the lecture today, I will finish all the topics about the flexible pavement design. And also, depending on whether you have time, I will just leave some several minutes for you to ask the questions. Okay, you can feel free to leave a message in the meeting chat or raise your hand. I will keep monitoring about the whole meeting if there's any potential questions. Okay, so with that, I will start the lecture today. So in the last lecture, we have introduced the variables which we have to consider for the design of the flexible pavement, and we stop at the introduction about the coefficients for the structural numbers. Actually, for different layers, for the asphalt concrete layer, the base layer and sub-base layer, we have different charts to find out the values of the coefficient alpha 1, alpha 2, and alpha 3. And we also have some typical values about the materials we're going to use for the surface course, the base course, and the surface course, the asphalt concrete course, the base course, and the sub-base course, which would be alpha 1, alpha 2, and alpha 3. You can find out these typical values, which were shown in the last column, depending on the strengths. This kind of coefficient is highly related to the strengths, which will be related to the resilient modulus of the materials. You can just refer this one for the refer this values for the future design for the actual projects. This is the introduction about the structural number, and we also have another variable we need to consider actually for both flexible pavement design and the rigid pavement design, which will be related to the moisture contents, and that's the quality of the drainage. So we have to determine the quality of the drainage layers for the pavement structures. Generally, we have categorized the quality of the drainage system into 5 categories. So we have introduced these definitions previously when we are talking about the drainage system design. They will be categorized into the excellent, good, fair, poor, and very poor conditions depending on the durations to remove the water from the pavement system. And the drainage coefficients is actually assigned for each layer, and it's also depending on the quality of the drainage system. So it's under the 5 categories, and the coefficient is also determined by the percentage of the time the pavement structure is exposed to the moisture level approaching to the saturation. With longer for the region with more rainfall, and there will be more durations for the pavement structure to be under the and with the water to approach to the saturation level, then we will have the smaller drainage coefficient. So the for the percentage, it's categorized into 4 levels. Less than 1% is the region which is very dry, rarely experience any rainfall. It's between 1 to 5, 5 to 25%, and higher than 25%, where there will be a lot of rainfalls over the year. And with these two variables, the quality of the drainage system, the percentage of the time approaching the saturation, we can select the appropriate values for the drainage coefficient, which will be shown in this table. And this value will be applied for us to determine the thickness of the asphalt concrete slab layers or the PCC slabs, and so for the flexible and rigid pavement design. We're going to show you how we're going to use the these variables in the future slides. So with that, we have finished the introduction about all the variables you need to estimate for the flexible pavement design. And this page will show you the steps for you to do the estimation to design the flexible pavement, identify the thickness of each layers, the asphalt concrete layer, granular base layer, and sub-base layer. So in the design, at first, we need to determine the effective resilient modulus of the subgrade. This is very important. We need to find out the value of the MR for the subgrade, and then we have to identify the serviceability loss. What's the initial performance serviceability, the pavement serviceability? What's the terminal pavement serviceability index, and find out the difference, which will be the serviceability loss. And we also need to estimate the total. The second one, the delta PSI, and the third one would be estimated total number of the 18 kilopounds equivalent single axle load for the design period, which means that I need to estimate the traffic loading, the ESAL. And first, we need to identify the level of the reliability and the overall standard deviation, which would be the reliability of the pavement structure, and the standard deviation R and Z is related to the materials and also the traffic load that we're going to consider. And third, we have to determine the pavement structure number. So this one, we're going to show you how to determine the pavement structure in the next few slides. And then last, we're going to use the structure number and the material type to determine the thickness of the pavement layer. This would be the ultimate goal. After the whole design, we want to show to the or write in the report to tell the contractor what's the thickness of the asphalt concrete layer, what's the thickness of the base and the sub-base layer for the project. And this will all be all the information we want to know for the whole design of the asphalt pavement, and is actually in the standard steps from the AASHTO 1993 method. Now you may have the questions about how we're going to do that. Once we know those information, how we're going to find out the thickness. And with that, we need to refer to the Nomograph, which is the graph generated by the AASHTO 93 method. With this graph, the graph is actually shown below. So this is just a Nomograph. With this is the graph which will give you the scales and some turning lines. With this information, with the variables that you estimated for the project, you can then using these variables and the turning lines to identify the structure number. And with the structure number, we can use the structure number and the coefficient factors to find out the thickness of each layer. So the Nomograph actually comes from the empirical relationship between the ESAL, the traffic load, that would be the W18, and the variables of the pavement design. In that equation, we have the relationship between the ESAL and the structure number, and this one can be the Nomograph will shows the solution from the traffic load. By giving the traffic load, the Nomograph will give the solution about what's the value of the structure number. If we are provided with the other variables, the ZR, S0, the also MR, and so on. So first of all, to go through the Nomograph, we're going to start from the axis on the left. So the one on the left is the first one is the reliability, and if we are provided with the reliability, say that if we are provided a reliability of 95%. So this is a 95%. You identify the reliability from this axis, the reliability axis. And also you're going to provide it with the standard deviation. Say that the standard deviation is, in this example, that will be 0.35. And so this is S0 equal to 30.35. R equal to 95%. Then with these 2 points, you're going to draw a line, a straight line, to connect these 2 points. And it will intersect with the first turning line. So the turning line 1. And start with turning line 1, say that this is a point A, the point 1. This is the point 1. And you will then go to check the traffic load. That will be the third axis, the ESAL. Will tell you how many millions of the traffic load for the design period. Say that if the traffic load is around, in this example, that will be around 5 million. Then you connect point 1 with the 5 million points in the ESAL axis, and draw a straight line. It will gonna connect to the second turning line, and they say that this is a point 2. And in the next step, it will be the resilient modulus. The resilient modulus of the subgrade materials, and you have to remember that this is the effective resilient modulus. You need to be adjusted with the seasonal impact. Well, if we say that the resilient modulus is it's 5, say that it's just an example, it's a 5,000 KSI. That would be the 5,000 PSI. With that, you're gonna connect the second point with the point you identified in the MR axis. You will get an intersection with the graph. So this is the with the intersection with the y-axis will give you the third point, and this is the point you have to use. And then next thing you need to think about is the design serviceability loss. And the design serviceability loss for this case is provided as let me see, it's provided as 1.9. And with that, you need to select the one. In this graph, each line will represent the serviceability loss, one serviceability loss. So the first one shows the serviceability loss of 0.05, and the last one shows the serviceability loss of 3.0. And if we know that serviceability loss is 1.9 for this case, that will be between the line of 1.5 and 2.0. It should be some place. Close to the line of 2.0. That will give you some position quite close to the 2.0 line. And with that, you can get the structure number. So the structure number for this case, for this one, is 5. So this is the this is how you're gonna find out the structure number. You get a structure number for as 5.0. This is for the process to calculate the structure number, and with the monograph, And we're going to use this graph to find out the structure number of all the layers, the asphalt concrete layer, the base layer, and subbase layer. And then we can use the relationship between the structure number at different layers and the coefficients to find out the thickness of the pavement, of the flexible pavement. So assuming that we are able to find out the structure number of each layer, we find out the structure, the surface course, the base course, and the subbase course through the nomograph. So this is what we get from the nomograph. And we want to identify the value of the thickness for each layer. So to do that, we're gonna start with the start from the first layer. We can find out the coefficient by the type of the materials. We can find out the coefficient for the structure number for each layer. We get alpha 1, we get alpha 1, alpha 2, and alpha 3. And the thickness of the first layer will be the ratio of SN1, the structure number of the first layer, divided by alpha 1. And this should be the minimum value. The minimum value. And you need to find out the closest value, which could be closest thickness, which can be higher than SN1 divided by alpha 1. And then once you have the thickness of the first layer determined, you're going to calculate the SN1 star. This is the estimated SN1 star. This is the estimated structure number of the first layer. And then you can use the structure number of the second layer to calculate the value of the thickness for the second layer. So that is SN2 minus SN1 star. So this is the estimated structure number of the first layer divided by alpha 2 times M2. And this will give you the value of the second layer, and you should be able to find out the closest value of D2, which should be higher than this ratio. And then you're gonna need to calculate the value of SN2 star. This is also the estimated structure number for the second layer, and it should be SN1 star plus SN2 star should be higher than SN2. And you need to find out what's the smallest value of SN2 star and try to get the value from the with the value of D2 star. And once you have the value of SN1 star, D1 star, and D2 star, and you can get the value of SN1 star and SN2 star, you can use the structure number of the third layer, the same process, and also the coefficient of alpha 3 and M3 to find out the value of D3. And again, the one on the right side gives you the minimum value of the thickness for the third layer. If we have more layers, you can still repeat this process, and it will give you the thickness of the other layers. But this is usually what we do for the flexible pavement with 3 layers: the surface course, base course, and subbase course. So with that, we have the whole procedure about the estimation of the thickness for each pavement layers. Also, there will be some recommended minimum thickness for the asphalt concrete layer and the aggregate base layers, depending on the scales of the traffic load. If the traffic is between ESL is less than 50,000, then we should make sure that the concrete layer is at least 1 inch and the base layer should be at least 4 inches. And if it's higher than 7 million, the asphalt concrete layer is higher than at least to be 4 inches, and the aggregate base layer should be at least 6 inches. This is an additional requirement regarding to the thickness you calculate in the you calculate based on the structure number. So if you get the structure number for the last case, when the ESA area is higher than 7 million, if you get a structure number around 3.5 inches, you have to choose 4 inches, because that's the minimum value we need to make sure we need to collect to make sure that the asphalt concrete can last for a longer time. So that's the additional requirement, and I know it might be a little bit confusing about all those variables, how to get all those variables together. So here I'm going to give you an example about how to use the monograph and what we can do to find out the thickness of the 3 layers. So here we're going to have the flexible pavement with the 3 layers, the surface layer, the base layer, and the sub-base layer. And we are provided with the modulus of elasticity, the values of the alpha 1, alpha I, mi, and we also know the ESAL is 18.6 million. We know the reliability 95%, S0 is 0.35, and the delta PSI is 2.1. We want to find out what's the value of the D1, D2, and D3. So first of all, we need to find out the structure number for each layer. So we have the monograph. This is the monograph we're going to use. You have to apply exactly the same scale of this figure. You need to find out the value from this figure. So first of all, we know that the reliability is 95%. So R is 95%. This is also this point, 95%. And the standard deviation is 0.35 is also this point. So we just draw the same line to this red one and get the first turning point. And next we find out that the ESAL, so this is the ESAL. The ESAL is 18.6 million. So you need to find out the value of 18.6. That should be this is 20. So it should be some place around here. And then you draw a straight line to connect with this point. And it will intersect with the second turning line. That will be the second point. And the next thing we need to do is connect the second turning point with the effective resilient modulus of the sub-base layer and the subgrade layer. And as we are talking about the first layer, so the subgrade we're going to use will be the no, this is not the subgrade layer. Sorry, this is just the effective resilient modulus of that layer. So the resilient modulus we get is 400,000 psi. So this would be the point here, 400,000. And I did not draw a straight line, but you need to get a straight line. Let me try to make it more precise. It's hard for me to make it precise. Okay. So this would be the point that you're going to intersect with the graph. So that's the third one, the PSI. The MR is 400 KSI, kilo PSI. And we also know that the delta PSI, the serviceability loss is 2.1. So it's 2.1. which means that we need to choose a line, draw a line which that is just behind the 2.0. That should be some line here. If we just draw a line here, you can find out the intersection, and with that you can get the I'm not quite sure whether I'm drawing everything accurately. Let me just see. I'm sorry, I guess I get something wrong for the selection of the MR. Sorry. So the one is not a 400. The MR, if you are talking about the layer 1, sorry, the layer 1, the MR value is the one layer behind you. So this would be the E2. So that should be 30 psi, 30,000 psi, and that should be the point here. That's the reason I get a very weird result. I guess should be a little. So this.
Sorry, I have a question.
Yes, yes.
So what's the MR? MR equal 5,700 psi.
Yeah. I that's what I just want to explain to you. So if we are using, now we are working on the first layer, right? So it's a layer 1. Layer 1. So if you are working on the layer 1, the MR should be the resilient modulus of the layer behind you. So in this case, that will be 30,000 psi. And if we are working on layer 2, you're going to use the one behind you, that will be 11,000 psi. And if you are working on the layer 3, that will be the MR. That will be 5,700 psi. So this is something I just what I just made it wrong previously. Is that clear to you?
Yes, thank you.
Okay. So just remember that always use the resilient modulus behind you. So in this case, I get the layer 1. The one behind you is 30,000, and you need to choose the delta psi equal to 2.1 as what is specified. So you get the value around I guess it's some point. And it should be some point around here. So the should be some point around here. So what do we get? You have to make this very precise from the map. I'm using my pen here. It's not that accurate, but if you are doing the homework assignment or work on any similar problems, using some rulers to get a straight line, and then find out the exact value. So with that, the first one for the structure number 1 is 3.2. So that's for the structure number 1. And then you can work on the second one for the layer 2. All the things, all the reliability, standard deviation, ESA will be the same. The only difference is the MR values. For the second one, the MR will be the one will be the layer resilient modulus of the layer below. That will be the 11,000. So you need to draw another line to go to 11,000, and I did not get the exact value, but you can do it by yourself later. And then using the same thing, I'm pretty sure that I did not get the quite right very precise value. So basically we can find out the value would be around the SN2 would be around 4.5, And again, you can do that function for the third one, for the third layer with the MR of the subgrade. That is 5500, and then you can get the SN3 as 5.6. Well, you can work on this one. You can work on this one by yourself after the class about how to find out the structure number and to see whether you can get some value which are close to the one I specified here. And now the next thing you will have to do is trying to use the structure number to calculate the values of the thickness. So first of all, we have known the structure number SN1 equal to 3.2, SN2 equal to 4.5, SN3 equal to let me see 5.6. And with that, we can first calculate the thickness of the layer 1. So the for the first layer, we're gonna call the equation the formula we just introduced. That will be the SN1 divided by alpha 1. So SN1 is 3.2, and alpha 1 is 0.42. So it gives you the value around 7.6 inches. So this is the minimum thickness of the surface layer, 7.6 inches. But usually the for the design of the flexible pavement, the thickness will be rounded to every 0.5 inches or to every 1 inches, depending on the requirements. So the smallest one, which will be high, that will be higher than 7.6 inches, will be 8 inches, right? If we choose the interval of 0.5 inches. So that will give you the value of 8 inches. And with that, we can calculate the estimated structure number for the layer 1. That is A alpha 1 times D1 star. Gives you the value of 8 times 0.42. So the let me quickly check the result, the value. 8 times 0.42. That would be 3.36. 3.36. So that's the first layer. How you're going to find out the thickness of the first layer. And then let's go to check the second layer. For the second layer, the thickness is determined by another equation. D2 star should be higher than SN2 minus SN1 star divided by alpha 2 M2. SN2 we get is 4.5. SN1 star is what we estimated, 3.36. And we also have the value of alpha 2 as 0.14 times M2 as 1.2. That one give you the result as 6.8 inches. And we also want to make sure that D2 is rounded to every 0.5 inches. So D2 star will be the closest one, which is a smallest one, which will be higher than 6.5 inches. That will be 7 inches. And then we can go to the third step to calculate the thickness of the last layer, the third layer. But before we go that, we want to calculate the estimated structure number of the second layer. So the equation we're going to use is SN1 star plus SN2 star higher than SN2. So for that we can actually derive that SN2 star is actually alpha 2 times alpha 2 times M2 times D2 star. So this is what we get. And then we can go to the calculation of the D3 star. That is SN3 minus SN1 star plus SN2 star divided by alpha 3 times M3. And we know the value of the SN1. SN3 is 5.6 minus SN1 is 3.36. And for SN2 star, that will be 0.14 times 1.2 times 7 divided by alpha 3 and M3. Alpha 3 is 0.08, M3 is 1.2. It will give you the value as 11.1 inches, and this will give you the value of D3. The actual D3 star should be some rounded value, that is 11.5 inches. With that, you can get the thickness of all the layers, D1, D2, and D3 for the flexible pavement. Okay, so this is actually a very good example for you to get some practice about the flexible pavement. So do you have any questions about the about this design? Also about these questions about this example? Okay. Okay. If no, I think this will be all about the flexible pavement design. And I have another short section about how the actual method is modified and applied in Ontario for the design, for the pavement design in Ontario. The whole procedure will be exactly the same. The only difference is about how we're going to calculate the values of those of the variables to use the nomograph and to calculate the thickness. So this will go to the, guess I put the wrong lecture number. This will go to the lecture 26, the flexible pavement design 3. We were going to give you a brief introduction about what's the adaptation we're going to use in Ontario to design the pavement. Actually, for the flexible pavement design in Ontario, we apply the same procedure of the actual 93 method, but we do some slightly modification and get a new protocol, which is showing the MTO 2008 version to give you the standard protocol for you to design the road in Ontario. For the design in Ontario, with the flexible pavement design in Ontario, we're going to use all the parameters we defined in ASTO method. We have to consider the load equivalency factor, the truck class, the truck factor, the percentage of the truck in each class, and the Ontario truck models to calculate the traffic loadings. And this one is it's actually the major method that we're going to use for the design of the road in Ontario, and especially will be applied for the major arterials and the highways in Ontario. For most of the highways with the 400 highways in Ontario, like 403, 407, 406. 406 is different. 406 is a rigid pavement design, but for all the other 400 roads, they follow this protocol. in Ontario. And but there will be some exceptions. If there's a lot of heavy commercial trucks, then probably we will consider a different protocols. That's not the one we're going to use for the ASTO method. So this table shows the typical truck factor we're going to use for the load equivalency factor in the calculation of the ESL in Ontario. It actually follows the definition of the FHW vehicle classes. It will categorize the vehicle into 13 types depending on the number of the type of the vehicles, the number of the axles, and also the combinations of the axle and the tires. And you can see that for the small cars, the motorcycles, the passenger cars, and the 2-axle, 4-tire, single unit vehicles, the truck factor will usually be set at 0, which means that we won't consider their impact. But for the other type of the vehicles like the bus, the 2-axle, 6-tire car, trucks, and so on, we will assign some truck factors for them to calculate the ESAL. And also there will be we can also find out some typical truck factors for the major truck classes in Ontario, including the 2- and 3-axle trucks. The typical value is around 0.5, and it ranges from 0.05 to 1.0, depending on the load and the structures of the combinations of the axle and the tires and so on. And also we have the values for the 4-axle, 5-axle, and 6 and more axle trucks. There will be if you are assigned to do the pavement design, you will need to do a survey about the type of the class and then try to calculate the truck factor and estimate the ESAL. Another thing we need to consider is about the lane distribution factor. This one is almost the same to the ASTO method, but we have a slightly more categorization based on the traffic volumes. For the depending on the number of the lanes in each direction. For example, if there's only one lane, then there's no doubt the lane distribution factor is 100%. But if there are 2 lanes, we will usually consider the right lane as a design lane with more truck traffic. But depending on the annual daily traffic, if it's less than 15,000, then the lane distribution factor is 90%. If it's higher than 15,000, then the distribution factor is 0.8. It's 80%. And we have the lane distribution factor for the other number of the lanes and other amount of the daily traffic. And also regarding to the serviceability, in Ontario, we also have some definitions about the serviceability index. And for the new constructed pavement, the PSI will usually be set around 4.5 for the freeways, and arterial corridors for the local road that will be smaller, could be around 4.2 to 4.4. And for the rehabilitation, which will be the maintenance of the road, the initial PSI could be smaller, between 4.1 to 4.5 for the highways, arterial corridors, but for the local roads could be 3.9 to 4.4. And the terminal serviceability also varies. For the major road, we have a higher requirement. We want the PSI to be larger. For the local road, it will be smaller. It could be as low as 2. With the initial and terminal serviceability index, we can find out the serviceability loss, which will be applied for the implementation on the Nomograph. And in Ontario, we also define another variable, which is called the pavement. That will be the next one, the pavement condition index, the PCI. We are also provided with the initial PCI and terminal service PCI. This one will be will have the larger range from 0 to 100, which means that it can give you a continuous index about the performance of the pavement. These two will, the PCI and the PSI will actually be equivalent to each other. You can observe the similar trend about how the PSI or PCI is changing over the time. And usually after certain years, you will once you reach to the condition for the rehabilitation, you will observe the significant drop about the PCI or PSI. In that sense, if you are the manager of the city, you will probably want to start the reconstruction at this point with the rehabilitation, because at that time you only need to spend less than like probably, for example, for $1 to make the road, improve the performance of the road back to the 4.1 or 4.2. But if we continue let the system run for like only 1 or 2 years, and you do the reconstruction, then probably need to spend 4 or 5 times more money to get back to the similar performance of the pavement structure. So that's the reason we always want to monitor the serviceability of the pavement and try to do the maintenance as early as possible to reduce the cost, to control the budget for the pavement design. I guess I don't have time to finish all the rest contents about the difference between the MTO and the ASTO method. I will continue this one in the next lecture. And if you have any questions, just feel free to send me email. I guess with that, I will close the meeting today. And do you have any questions for now? Okay. Well, if you don't have any questions, I guess that will be all about the lecture today. And it takes longer than what I expected, but I'll try to finish all the rest of the contents in the next lecture and introduce the rigid pavement. Okay, if you don't have any questions, I will close the meeting today, and I really appreciate your attendance. And just feel free to let me know if you have any questions, and I will see you on Wednesday.